Data in a computer is represented as zeros and ones. How do we have such diverse objects as videos, music, emails, postings, tweets, bank transactions and cryptocurrencies?
Moreover, we can also represent behaviors in a computer. For instance, we can program them and define actions for an agent to act on our behalf at eBay.
The transformation from analog representations of many objects to digital representations requires two fundamental steps.
First, we encode the desired set of information objects as an enumerated list, and then associate a number to each item in the list.
For example, the letters, and most common punctuation symbols, in a sense, the character of an English keyboard, are encoded as ASCII values since the 60s.
In this coding of the keyboard symbols, the capital S corresponds to the value 83. To introduce the binary representation of natural numbers, we start with the familiar representation in base 10.
Human civilizations have used many other systems. For instance, the Babylonians used base 60.
When we write numbers today, we use 10 symbols: 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9.
These symbols represent their value alone, but as part of a number, they contribute their value differently.
A 1 followed by 0 is not the same as a 0 followed by a 1.
Each position to the left is the next power of 10.
Thus 1, 0, 0 corresponds to 100, and 1, 0, 0, 0 corresponds to 1000.
If the symbol is different from 0, then we need to multiply the symbol's value by the power of 10 for that position.
This is also the case for the position immediacy to the left of the decimal point, which is for 10 to the power of 0.
The positions to the right of the decimal point continue decreasing the power of 10 by 1.
Thus, 2 followed by 0 and 0 is 2 times the second power of 10.
The string represents 2 times 100, or 200.
But 2 followed by 3 zeros is 2 times 1000 or 2000.
The zeros also participate, but multiplying the corresponding power by 0 does not contribute to the total value we are representing, but they hold a position.
A point followed by 2 means 2 multiplied for 10 to the minus 1, or 1/10. Thus, this is 2/10 or the fifth fraction of 1. In binary representation, we replace the base at 10, 4, 2, and we have only two symbols, 0 and 1.
These two symbols are named binary digits, or bits for short. Thus, the positions are now placeholders for the powers of 2.
The 0th power of 2 is 1. The first power of 2 is 2. The second power of 2 is 4. The third power of 2 is 8. The fourth power of 2 is 16 and so on, doubling each time we move one position to the left.
Since moving one position to the right removes one factor of 2, the negative first power of 2 is 1/2, and the second negative power of 2 is 1/4, and so on, always dividing by 2 for one position further to the right.
Therefore, we have an easy way to convert from binary to our usual decimal values. We interpret the given string of zeros and ones.
For example, the string 0, 1, 0, 1, 0, 0, 1, 1 has a 1 in the 0th position. This last bit contributes a value of 1.
In the first power, we have another 1, so we have a 2 added to the total value. We are up to 3.
The position for 2 to the 2 and the position for 2 to the 3 have a 0, so we have no contribution here.
But the position of 2 to the 4, which is 16, does have a 1, so we add 16 to the running total.
The place for 2 to the 5 has a 0, nothing to add for this one. But 2 to the 6 has a 1, so we add 64 to the total.
We have accounted for all the positions that have a 1, and that could have some impact. Since 64 plus 16 plus 2 plus 1 is 83, our string represents the value 83. This happens to be the code for the ASCII character S.
Decimal notation has the property that shifting the decimal point by one position has the effect that the value represented is multiplied by 10 or divided by 10.
But, in base 2, shifting right one position divides by 2, while shifting left one position multiplies by 2.
How can we find the binary representation of a positive integer number?
One recursive algorithm goes along the following approach. Since all places of the binary representation are powers of 2 except the 0th position, this place represents whether the number is even or odd.
Thus, when the positive integer number is odd, we know the rightmost bit is a 1. If the number is even, the rightmost bit is 0.
Moreover, if we divide our number by 2, the representation we are trying to find has shifted to the right by 1 position.
Ignoring the fractional part, which only exists when our number is odd, we can check if the result is even or odd to determine the next bit to the left of what we have found so far.
We repeat this until we reach the value 0. After that, we know all bits to the left are 0, and we do not write them.
Interestingly, if we count how many repetitions the algorithm took to find the leftmost bit different from 0, we have calculated how long is the binary representation of this number, or 1 more than the logarithm base 2 of our value.